evening, everyone. Quick bit of housekeeping. You've got a dashboard with an arrow, a white arrow pointing left. If you click the arrow, it will point right, and then you'll find you've got your dashboard, and down near the bottom you've got a bar that says questions. And if you click on that, you will then get the panel which will allow you to type in your questions. Right then, having got that out of the way, I'd like to introduce tonight's speaker. This is our 8th BCS Open Branch meeting, and tonight we're going to examine how safe need a driverless car be. Our speaker for tonight is Dr. Siddhartha Kaskir, I hope I pronounced that right, who's head of the computer-aided verification at Warwick Manufacturing Group, which is obviously part of the Warwick University. So without further ado, I'd like to hand over to Siddhartha.
Perfect. Thanks a lot, John, for the introduction. I'll try and share my screen. And let me know if you can see my presentation. Okay, perfect. Okay, perfect. Very good evening to everybody who has joined us for this talk. So I'm Siddhartha Kaskir, as John said. I'm leading the verification and validation research for intelligent vehicles at WMG at the University of Warwick. And today I'm going to talk to you about how safe does a driverless car need to be. And I'm just trying to figure out how I make this work. Just if you bear a moment with me. Yeah, I think I should be fine. So I'm going to talk a bit about how safe does a driverless car need to be. And the whole premise of this talk is to open you to this myth that driverless cars are going to be absolutely safe, which is not going to happen. And how can we actually deal with this concept that driverless cars will never, ever be absolutely safe, but we still can reap a lot of these benefits, a lot of the benefits from this technology, and how do we go about doing that? So I'll do a bit of introduction in terms of why we are actually talking about driverless cars. Is it even a good thing to talk about them? Is it a good thing to invest so many millions and billions of pounds of government money in the research? And then introduce a concept of trust in automation that is fundamental for us to reaping the benefits of this technology. And then introduce a concept which tries to provide a way out of this myth of absolute safety. It's a concept that we coined around informed safety, and we'll talk a bit about the aspects associated with informed safety, and then we'll hopefully summarize the talk with a few action points for all this audience members today. So we are all engineers on this call, even if you're not. A lot of us who like and love numbers. So let's talk a few numbers when it comes to connected and autonomous vehicles, or driverless cars, or self-driving cars, whatever you want to call them. So it is said that in order to prove that driverless cars are safer than human-driven vehicles, they need to be driven for 11 billion miles. Now, to be very specific, it's not even saying that it is absolutely safe. It's only 20% better than human-driven vehicles. And just to prove that, we need to drive them for 11 billion miles. Now, to put that into context, that's the same as driving to the moon and back 20,000 times. Now, that's not a realistic proposition. So we can't do that in a efficient or economically viable manner. However, there's another very interesting number that is doing rounds around this technology, and which says that if we can introduce automation or driverless cars, which is even 10% better than human-driven vehicles. One thing to note here is it's talking about just 10% better. So even if we can introduce something that's 10% better, in the next 30 years, we can save over 100,000 lives. Now, that's a very big motivation for us to introduce this technology and not wait for it to be absolutely safe, because we've just discussed that we can't prove that it's going to be absolutely safe. We can't do those kind of numbers like 11 billion miles. But another very interesting number here, which is even more surprising when it comes to technology, is even if we provide this technology, let's assume we are in a utopian world when we have absolutely safe automation and we provide this technology to users, would they actually use this technology? Research suggests that that's not the case. So around 50% of the drivers who were presented with the current driver assistance systems as part of the cars that they bought and paid extra for this kind of technology, they did not use this technology around 50% of the time. Now, that's a very interesting number, because we can introduce a technology, but if we cannot get the drivers or the users to use this technology, there's no point in us introducing them, because we're not going to reap the benefits. So how can we actually get people to use this technology around automation? And the key aspect over here is the intertwining of safety and what we call as trust in automation. So we did a lot of work at WMG at the University of Warwick, trying to understand what does it take for users to trust automated vehicles or automation in vehicles. And we found out that trust as a construct is a multifaceted construct. It's got various aspects that are actually influencing the development of trust in automation from a user's perspective. And why are we even talking about trust is because in order to get a user or a driver to use this technology, trust is the biggest component that influences that decision. So if we can get people to trust this technology or trust automation, then we can get them to use this technology. Now, we would not have the time to go through each and every factor that is influencing trust in automation. So we'll talk about one aspect around safety, and I will point you to some of the other publications that would take you on this journey of the other factors that influence development of trust in automation. So the factor that we're going to talk to you about today is certification. Now, how does certification lead to trust in the system, and how does it influence the driver's use of the system? Now, certification is all about proving that a system is safe. Once a system is certified, we are reassured that that system is safe. A very common analogy, which is very timely right now. None of us know how do vaccines work, but once a vaccine has been approved by a governmental agency, we trust that those vaccines, these COVID-19 vaccines, would serve the purpose for us. Very similarly, if we've got a technology certified, that gives us the inherent trust that this technology is safe. So how do we go about proving that this technology is safe or not, especially when it comes to driverless cars? So the question here we are trying to answer is, how do we establish safety of a driverless car? The first thing I would say is absolute safety is a myth. As I've just mentioned earlier, that we can't even prove that a driverless car is 20% better because we can't drive 11 billion miles. So trying to prove it is absolutely safe is completely out of the question. So let's not even pretend that we're going to prove that driverless cars are safe, absolutely safe. However, it is still possible to ensure safe use of this technology of driverless cars, as long as we can establish and communicate the true capabilities of the driverless car. And more importantly, we can establish and communicate the true limitations of the driverless car, or any automated vehicle that you might find. So the goal for us as engineers is not only to establish the true capabilities and limitations, but also find a way that we can communicate these to the user so that we can ensure that there is a level of trust in the technology, but more importantly, we can ensure that the driver uses this technology in the correct manner. So that prevents misuse or abuse of the system, which can be even more harmful than just providing them the technology itself, because they can use it in ways it's not designed, and that can be fatal. And there have been cases in various parts of the world where technologies have been used in ways that they've not been designed for, and that has led to fatalities. So now our goal is to somehow establish the true capabilities and limitations. And once we do that, then we'll come to how do we actually go about communicating them. So let's just first talk about this concept of how do we go about establishing true capabilities and limitations. And that where we bring this concept called informed safety, where we are actually trying to understand the true capabilities and limitations. And when you try and subdivide this question of trying to understand this, you can establish three different and distinct aspects that we need to be working on. The first thing we need to do for any automated vehicle or any driverless car is to understand where does it operate. The second thing we need to do is understand how does it operate. And the third thing we need to do is have some evidence of the claims that we are making of the first two things, like where does it operate and how does it operate. So these are three things that we need to do to understand the true capabilities and true limitations of the technology. Now, what does that translate into in terms of more engineering terms? So where does it operate essentially means that we're trying to understand the operating conditions of an automated vehicle. How does it operate essentially means we are trying to understand the performance requirements of the automated vehicle. And the evidence of both these evidence of the claims for both these things is essentially the verification and validation evidence that we have to create as engineers. So from an engineering standpoint, all we have to do is fairly simple, these three things. But as soon as you start doing them, that's when you appreciate the nuances in them, and that's where the challenges are. And we'll go into some of those challenges today. So let's start off with the first block over here. Where does it operate? In an driverless car context, where does it operate is a big challenge to define, because of this concept that has been introduced, what we call as operational design domain, or ODD. An operational design domain essentially means defining the operating conditions under which your automated system, or a driverless car, or even a lower levels of automation can actually perform in a safe manner. The challenge here is these operating conditions can be defined in n number of ways. You can talk about the environmental aspects, you can talk about the geographical aspects, you can talk about the time of the day restrictions, and the list goes on. So the biggest challenge right now we have from a safety perspective of a driverless car is actually to define the operational design domain. You might think that it's the most trivial task, that you've designed something, you should know where it operates. But when you're trying to operate on real world roads, the level of uncertainty is very high. So trying to design your system to all probabilities and all possibilities is a challenge that we are facing as an industry. So one of the tasks that has been taken as part of this industry is trying to create a methodology of how do we go about defining the operational design domain. And before we do that, let's just talk a bit about why is it so important to define the operational design domain. So we've already established that we can't drive 11 billion miles. Okay. However, let's assume that we could. Let's assume for a second that we could. Driving 11 billion miles up and down the Nevada desert is not going to give you anything if you want to deploy your driverless car in central London. So essentially, the number of miles, even if we could drive, is not a realistic or a reasonable metric to use. So there is this shift that is happening now from number of miles driven to types of scenarios experienced by a driverless car. Now that's a good progression in thinking. However, the types of scenarios that a driverless car would experience in Phoenix, Arizona would be very different to the types of scenarios it would experience in central London. So just trying to define scenarios is not good enough, because we need to make the scenarios that we are using for the tests as a function of the operational design domain. So if we are going to deploy our driverless car in Phoenix, then the scenarios against which we need to be testing the system should be very different to the scenarios that we should use for testing in central London. And to take that argument one step ahead, let's assume a very similar application of an automated driving system. So here's two automated driving systems. Both of them are low speed applications. One is being deployed in a city center, and the other is being deployed on the air side of an airport. Both the systems have been manufactured and developed by the same manufacturer. However, the scenarios that should be used for testing both these systems would be very different, because the ODD, or the operational design domain, of both these systems is very different. So that's one of the key reasons why defining an ODD is key to trying to establish the safety of an automated driving system and essentially the driverless car itself. So we've talked a lot about the importance of an ODD, or an operational design domain. Let's just talk about what exactly is an ODD. So we've done quite a bit of work in this area together with various stakeholders in the UK on a British national standard called BSI PAS 1883. BSI PAS 1883 provides a taxonomy of attributes that we need to use to define the operational design domain. So here you can see there are three types of attributes that we use to define an ODD. You've got the scenery side of things, which is everything that is geostationary in my environment is in my operating condition is scenery. So that involves things like traffic lights, that involves the road structure, that involves things like the road markings, the motorway gantries, and everything that is geostationary. The other type of attributes we have is environment, things like weather, things like illumination, particulate matter, connectivity. These are part of the environment set of the attributes. And thirdly is what we call as dynamic elements. And that's where we include things that move around you. So things like traffic participants, like pedestrians, other road users like vehicles, and also the maximum allowable speed of the driverless car itself. So a classic example over here could be that I have designed my driverless car to operate up to a top speed of 40 miles per hour. However, my system cannot operate in an area where there are pedestrians. So here, when I'm defining my operational design domain, then I'm explicitly stating that I cannot handle pedestrians. So if anybody is trying to deploy their driverless cars, the first thing they need to check is where they're deploying that technology. Would pedestrians be present in that area or not? If yes, then you should not be deploying that driverless car in that area, because that system cannot handle pedestrians. So that is one of the key reasons for being able to define an ODD in an elaborate manner, because that would guide a lot of the decision making process around should we or shouldn't we allow driverless cars to be deployed in a particular area. And once you've defined the operational design domain itself, the next important aspect that one needs to be aware of is, from a driverless car perspective itself, it needs to be aware of each of the attributes that have been used to define the operational design domain. Essentially, let's take an example. Let's talk about rainfall. Let's say that my automated driving system or my driverless car cannot handle rainfall more than, let's say, 10 millimeters per hour. The question is, how does the automated driving system, or how does the automation or the control system know what rate is the rainfall? And what exactly does 10 millimeters per hour of rainfall mean? Does that mean that I should put my hand out of the window and measure if it's 10 millimeters per hour? Or does that mean that I can wait for a roadside unit to tell me the rainfall rate? Or does that mean that I subscribe to some online application that looks through the weather maps and the radar maps and gives me a number? So one of the key aspects over here that we are trying to understand is, how do we go about measuring what we are using to define the operational design domain? So I can say that rainfall is in or outside of my operational design domain. However, how does the automation system or the driverless car establish if that is true or not? So that mechanism is something that is still being developed. So while we've done some work in trying to understand how do we go about defining this, there's still a lot of work we need to do trying to understand how do we go about trying to measure what we've defined. Now, from a human perspective, that must be sounding very, very trivial. When we drive the cars, we know if it's raining or not. We know if it's heavy rain or not heavy rain. But when you try to imagine that this awareness needs to be imparted to a machine, you would start appreciating how sophisticated the human brain is, or how sophisticated human beings are, that we can do this process in a very, very simplistic manner and very, very instinctive or intuitive manner. Let's take another example. So we've spoken about rainfall. Let's talk about, let's say, scenery elements and dynamic elements. So I might say that my driverless car can only operate if I have at least 4 lanes on the road. Let's make that as a hypothetical driverless car definition. So I need 4 lanes at least on the road for me to be able to drive safely. Now, how does the driverless car know that there are 4 lanes on the road or not? So one of the possible solutions for that would be to use high definition maps. There are lots of high definition maps that are now available that give us up-to-date information about if there is one lane or two lanes or three lanes, etc., etc. Very similarly, if I want to know how dense the traffic is, because you might say that the operational design domain definition of my driverless car could be that I can operate on the motorway safely as long as there are no trucks on the motorway. Now, that's a very legitimate definition for an operating condition of a driverless car. How does the car know in real time that there are no trucks on the motorway? So that's where something like a traffic management system can provide the information over the air to the driverless car to say, look, I believe 100 meters from here, from where you are, there is a more truck. So that's where the driverless car could stop, saying, now I'm outside my operating condition, I cannot operate, so I need to stop. Or it could actually also say that I have checked the motorway at least up to 10-20 kilometers before and after where you are, and there are no trucks. So then you can actually operate safely. So there are ways where we can actually get the awareness of the operational design domain to for the vehicle or for the driverless car itself. But there's some aspects that are still under consideration, and especially the environmental aspects is where we are facing a lot of the challenges. Having said that, a lot of these attributes that I've mentioned could have their own interpretation. So what might be heavy rain for me may not be heavy rain for you. It might be light rain. Now, people living in Coventry are very familiar with rainy days. So for us, rain might be a common thing. Now, what might be light rain for us in Coventry might be very heavy rain for people in Phoenix, Arizona, where it hardly rains. So in order for us to speak the common language, there is a need for standardization across the board, not only nationally, but also internationally, so that when we are developing systems, we are developing them to a standard that all of us agree to and use as part of our development process. So there are lots of activities that are ongoing at various national and international levels, like BSI and ISO. But the important aspect that we are working on is to ensure that while it is good to have so many standardization bodies involved, we need to prevent the creation of any competing standards. So a situation that we absolutely do not want is a British standard being created, which is contradictory to an international standard that was being created in parallel. So there is a need for harmonization across the board in this area. So one of the activities that I would like to talk to you about today is an activity that was undertaken in the UK, where we've created a taxonomy for an operational design domain. And it was a standardization project that started back in October 2019, and the standard was published last year. But the important aspect over here I want to mention is what made this project so unique. We talk a lot about in our normal lives about diversity, about inclusion. Standardization is no different. In order to get a strong standard, we need to ensure that we are representing the viewpoints of a diverse set of stakeholders. So a lot of the times people tend to think that the standards need to be created by people who are actually developing these driverless cars or who are actually involved in the software coding. That's not the case actually. So if you look at the kinds of stakeholders that we have for this activity, we've got these traditional manufacturers or these developers of these automated driving systems. We've even got local authorities like Oxfordshire County Council. We've got the Met Office. We've got the insurance providers, and we've got the academic organizations. So it is very important that any standardization activity that takes place has the appropriate representation and the diversity in the stakeholders that are actually creating that standard. And that actually made this work in the UK fairly unique, because we were the first to have such a diverse set of stakeholders that led to a creation of a standard in this area. Having said that, so we've spoken a lot about operational design domain. How does that fit into the wider verification and validation pipeline? So we've mentioned that absolute safety will not exist. Okay, accepted. But we've at the same time we've mentioned we still need to create this level of informed safety, which means we still need to establish the true capabilities and limitations. And defining the operational design domain is only the first aspect of that. Once you've defined that, you still need to test if what you've defined is actually what the system is doing. And that's where the verification and validation comes into play. Now, if you think about verification and validation across the board, now let's not even talk about driverless cars. If you talk about any domain that you're interested in, the verification and validation pipeline essentially involves only three things. It needs scenarios, test scenarios that you would like to execute in an environment. It could be simulation, it could be real world. And you need a way to use the output of that test execution as part of your safety evidence to make an argument that your system is safe. So there's only three things that you need, irrespective of your domain, irrespective of the complexity of your system. There's only three things that you need. If you take that a step down, from a scenario perspective, we need to create those scenarios. And we've already mentioned that those need to be a function of the operational design domain. You need to format that scenario in a particular language that all of us understand in the same manner. We need to store those scenarios in a particular repository. Otherwise, we will be reinventing the wheel again and again. And once we've done that, then we plan and execute those scenarios and then analyze and decide if my system is safe or not. Or I will qualify myself. We analyze and decide what are the true capabilities and limitations of the system. So let's talk a bit about the scenario side of things first. So when you talk about scenario generation or scenario-based testing, the first aspect that we need to do is how do you go about generating scenarios? So we've already mentioned they need to be function of operational design domains, but how do you actually go about creating this individual scenario itself? So we've got a hybrid methodology where we use a data-based approach and a knowledge-based approach to generate these scenarios. So from a data-based approach, we analyze accident databases to understand which type of parameters or understand the trends for understanding the parameters that led to the accident itself. At the same time, we also analyze the insurance claim records to understand the trends that led to the near miss events around the insurance claims. So those two are what we call as data-based approach. You might notice that up until now, I have not mentioned that this is for a driverless car domain or this is for a driving domain. This approach is agnostic to the driving domain. You could have a data-based approach in aviation, in marine, in any domain where there are autonomous systems. The other approach we have over here, the third one, is a knowledge-based approach. Here, we are actually analyzing the system design itself to understand how the system would fail. And these three methodologies provide us with lots and lots of scenarios. And once we've got them, we need a repository for storing these scenarios. And that's where we created the Safety Pool Scenario Database, which is the world's largest database for scenarios when it comes to driverless cars or automated driving. And the key aspect over here, as I mentioned earlier, we need to be speaking the same language. So we've created essentially a format to define the scenarios also. So all the scenarios that are there in the safety pool scenario database are defined in a standard format so that everybody understands these scenarios in the same manner. So we've created now the scenarios, we've stored the scenario, we've formatted the scenarios. The next step over here is actually storing that scenario. So I'll talk a bit about the safety pool scenario database itself. So what is the scenario database and what does it do? Now, the scenario database is actually a secure repository for scenarios for different types of operational design domains. And one of the key aspects of this database is that it meets the requirements of different types of stakeholders, be it the cab developers or the manufacturers of the automated driving systems, be it tier one suppliers, people who provide just the software, be it regulators or governments, or be it academic organizations or researchers. So it's open to all these type of stakeholders. And the key aspect that we had to do over here was these stakeholders had competing requirements. So when you've got competing requirements, it's fairly hard to try and please all of them. So we had to come up with some genuine solutions so that we met the requirements of all of these stakeholders. So before, we've spoken a lot actually today around scenarios, but we've not yet talked about what a scenario is. So essentially, a scenario that we use for testing or we use as a part of a verification and validation has three different things. It has got the scenery, it has got the dynamic elements, it has got the environment. You might say that's the same three things that are in an ODD definition. However, actually you are right, they are the same three things. However, for a scenario, the additional aspect is that the dynamic elements also have their behavior defined as a part of the scenario. So for example, a vehicle cutting in front of me on a motorway is a scenario because I have defined the cut-in behavior of the vehicle in front of me. So that essentially is a scenario. Now, how do we use that definition as part of the wider VNV stream? So we've just said that there's lots and lots of scenarios that would be out there. So the safety pool scenario database itself has got 100,000 scenarios. Now, trying to efficiently search the scenario database is something that is the need of the hour when you've got so many scenarios. So one way to do that is map the scenarios to the corresponding operational design domain. So again, we keep coming back to operational design domain because it's kind of the pillar of the whole safety assurance process for a driverless car. So let's take one example in the interest of time. We've got this city center where we could use the BSI PAS 1883 taxonomy that we created for operational design domain and say this city center is characterized by pedestrians, cyclists, passenger cars, and a shared pathway. So these are ODD tags or ODD labels that then we could use to query the database to identify what types of scenarios are relevant for this use case for me or for this ODD. And then I can actually test those scenarios only. So it enables me to shrink from 100,000 scenarios to only the ones that are relevant for me. So that's another very important use case for defining the operational design domain. So in the interest of time, I'll skip a few of the things over here, just to give you an understanding. So the labels that we use for a scenario could be not only be the operational design domain labels, it can also be things like, is it for a manufacturer A or is it for a manufacturer B? So there's also metadata associated with the labels over here. So one of the things I want to also mention, now that we've defined these scenarios, we formatted them in a particular language, we've stored them as part of a scenario database. The next thing is to plan and execute the scenarios in either simulation or in real world, and then analyze and decide the capabilities and limitations of the system. The whole pipeline that you see over here, create, format, store, plan, execute, analyze, decide, each aspect needs to have an alignment with standards, again, so that we can speak the right language. So there's, oops. There's a lot of activity that is ongoing right now in an ODD landscape, in a scenario landscape, but we need some more activities around the planning and executing and analyzing and deciding side of things. So those areas are still fairly, I won't say immature, but they're still on the path to development before we can actually do the standardization for those kind of activities. And it is only then that we can start thinking of a day when we will have driverless cars on road. So if anybody tells you that we are going to have them tomorrow or day after or later this year or early next year, they're more or less not being true to you, because that's not going to happen, because there's so many other challenges that I've already mentioned to you. So we've been very fortunate that we've been involved in lots of these standardization activities. So some of our key learnings from those activities is know when to start. So one thing that is very, very important is you should not be standardizing something that you do not know enough about. At the same time, you should not be standardizing in a way that stifles innovation. So there's always a sweet a point at which you start the standardization activities, when you know enough and you can standardize in a way that you don't stifle innovation. At the same time, no one organization can do standardization on its own, on their own. So that's a key requirement for standardization, is collaboration. So there is a need for more and more collaboration in this area. And most importantly, there's a need for communication. So if you go back to one of my earlier points, that not only is it important to establish the true capabilities and limitations, it is also important to communicate those true capabilities and limitations. And that's where the need for communication comes in. And why are standards needed? So you might say that as engineers, we are all about just creating the technology. Why do we need to spend time on standardization? Why do we need to spend time on driving consensus? Not only does it help to consolidate the state of the art and allow different types of manufacturers and different stakeholders to talk to each other, but the most important thing, according to me, what it does is it prevents unsafe introduction of technology. And that is absolutely key when you're working with an emerging technology like driverless cars. The reason for that is the first accident or the first PR disaster that might happen could be detrimental to this whole technology and the whole industry. Sometimes what I tend to say is, what we do not want in a driverless car industry is to have the fate that genetically modified crops had, that GM crops had. Essentially, it was a technology that was not communicated properly. It was a technology that was not, the true capabilities and limitations were not addressed and communicated, and that's what led to its death. So we don't want that to happen from a driverless car perspective. And that's the reason why standards and regulation are really, really important. So in summary, I would like to say, taking the point from the last couple of minutes, standardization and regulation are key enablers for developing trust in automated driving system. So the first point we mentioned, that development of trust, and we focused only on the certification side, which is associated with standardization and regulation. So it is key, but it's not the only thing. As I mentioned earlier, trust as a concept is a multivariate construct. And we can have appropriate trust or accurate trust, but we need to be aware and conscious of the fact that absolute safety will not exist. So if we are blindly trusting the system is safe everywhere and anywhere, then we are fooling ourselves. But we can still use it safely and reap the benefits if we can establish the true capabilities and limitations of these automated driving systems. And that would enable us to create this safe state of informed safety. And from a perspective of how do you create these this state of informed safety to and establish the true capabilities and limitations, a lot of our existing verification and validation processes need to be adapted for automated driving systems. And we can only achieve this position if we collaborate, if we share knowledge amongst each other, both nationally and also internationally. And that brings me to the end of my talk. I'm happy to take any questions or comments that you might have. John, would you be moderating the questions?
I will, yes, but nobody's entered any yet.
Okay. I will stop sharing my screen.
Okay, right. Just explain to everybody that you're double muted. You're muted by the GoToWebinar tool, but you're also muted at your end. So if I see Dan Abbasi has raised his hand, so if I unmute Dan Abbasi.
Hi, I think I've been double unmuted now.
Yes, you have. So
Hey, John,
you have a question?
Yes, I do. Thank you very much, Siddhartha. Interesting talk. I was just wondering, at the beginning, it did indicate that AVs are 20% better than human drivers. I was wondering, in what environment was this test carried out? Was it with human drivers as well, or with just AVs alone?
Okay, so that's actually not even a test, to be honest. That's a statistical argument that has been created based on the analysis of the number of fatalities that humans have when we are driving as part of our own in a normal manner. And in order to prove that if we had a hypothetical world where there were only AVs, then it would at least take us these many 11 billion miles. So it's not actually a real test. It's actually just a statistical argument.
All right, thanks.
And Margaret's asked a question. 1917. Is the British standard 1883 for manufacturers or consumers?
It is actually, depending upon how you classify consumers, it could be classed as it is for both. So that is one of the reasons why we had local authorities on the stakeholder team that actually created the standard, because the local authority is the one who approves a particular automated driving system for deployment in their area. So they need to understand as to how one needs to define the operational design domain. So in that case, they are the consumer of the standard, and that's the reason they are also involved as part of the development process. Having said that, an abstraction of the operational design domain could be used to convey the capabilities and limitations to the society at large. So for example, if I say that my operational design domain definition for an automated driving system has only city center roads on sunny weather, then that then needs to be communicated to the society who are going to use that technology in order to ensure that they use it in a safe manner.
You're right. Shadman Rafid has got his hand raised, so I'll try and unmute him. Shadman, can you unmute yourself?
Yeah, I think you can hear me now.
Yes.
Yeah, so I had a question regarding the standards that you talked about. and the ODD. So given that the ODDs are so different in different conditions, so for example, Phoenix, Arizona versus Central London, how easy or difficult would it be to unite all these standards together for, to have that one sort of operating system to, unite all these together? Because let's say if I'm living in London, but for some reason I need to travel to Arizona with the vehicle that's standardized in London, how, what happens then?
So that's a brilliant question. What we are standardizing is not the system design, it's the way you define your system design. So we are not standardizing the different operational design domains. We are standardizing what you need to use to define your operational design domain. So if you've got a system in central London, absolutely you cannot use it in Phoenix, Arizona, because it will need to be recertified, retested for Phoenix, Arizona, because it's a different ODD. The standardization activities is actually to get people in Phoenix speak the same language as people in central London.
I see. Got you.
Yeah. And it's not a trivial activity. It's not easy to get people to speak the same language.
Cool. Thank you very much.
Naomi has asked, how many years do you think that it will take for me to have a driverless car to use to get to work? For example, Rugby to Nuneaton.
I do get this question every time I give a talk on this subject. So the answer I tend to give is, depending on the operational design domain, it could be a few years or it could be a few tens of years. So if you've got a low speed application, I'm not very familiar with the route between Rugby to Nuneaton, but if you've got a route which is a low speed application and fairly constrained, then I would say 5 to 6 years and you should have the technology on the road commercially available. If you're talking, let's say, London to Newcastle, that's not going to happen in the next 10 to 15 years. So that's the kind of time frames we're looking at. So the more complex your operational design domain becomes, the more time it takes to actually get it on roads commercially available.
Any more for any more? Raise your hand or type the question in, please.
So there's one from Margaret, I think.
Yeah. Do you think manufacturers will collaborate on the production of technology supporting driverless cars?
I would say that production of technology could be interpreted in a number of ways. Based on our conversations with various stakeholders across the world, when it comes to safety, there is a wide consensus that safety for driverless cars need to be pre-competitive. And that's the reason there is a large number of international collaborative efforts ongoing right now when it comes to safety of driverless cars. I cannot comment much on non-safety aspects because that would be the USP of the individual manufacturers, but I definitely see manufacturers collaborating when it comes to safety issues.
Any more for any more? Margaret says thank you.
Thank you, Margaret.
Who's raised their hand?
Yeah, that's me. I did type my question. Probably you're not seeing it. I was wondering, where do government regulations, e.g. highway code, come into all these?
So that's a very interesting question because there's a lot of work ongoing on the highway code as we speak. So that is a topic that has garnered a lot of interest in the recent years. One of the reasons for that has been, how do you define good behavior for a driverless car? The highway code governs us as human drivers as to what we should be doing when we are driving on road. Does that apply to a driverless car also? I'll give you an example. So us as human drivers need to stop at a zebra crossing when there's a pedestrian standing next to the zebra crossing. That's what we all do. If you replace us as a human driver with a driverless car, does the driverless car stop at the zebra crossing? You might say yes. How long does the driverless car stop? The highway code has no definition for how long does it need to stop. If the pedestrian keeps on standing next to the zebra crossing without crossing the road, does that mean the driverless car will be stuck at the zebra crossing forever? Or does it actually creep slowly in front? So that's the bit that is being worked on right now in terms of how do you define good behavior or acceptable behavior for driverless cars. And that's where the highway code also comes in.
Thank you.
Any more for any more? Come on, I know you're out there. I can hear you breathing.
I'll be late in the evening for people now.
Yeah.
Naomi's asked a question. It's in the question list.
Yeah, spotted, yeah. Naomi's asking, has there been much discussion about barriers to driverless cars? What use, e.g. age, disability, people who have lost their driving license, etc.? Good question.
Yeah, it's a brilliant question. Honestly, I would say that there hasn't been as much discussion as there should be. But I would qualify that by saying there is an increasing level of discussion on accessibility and also on inclusiveness on the designs of the driverless cars. So providing mobility to the disabled, providing mobility to people who've lost a driving license is one of the main use cases and immediate use cases that we see as an industry as a benefit of this technology. However, we need to complement the technology development by the design side of things so that people with disabilities can actually get onto these vehicles and take that journey. And these two schools of thought are right now slightly disjoint. And there's a lot of work that is ongoing now, I would say more so in the last year or so, which is focused on bringing these two schools together.
William Richards has asked, so as someone who can't drive as a result of being visually impaired, the concept of driverless cars interests me. Are you saying I shouldn't get too excited about having a car that can drive itself?
Unfortunately, I would say yes, because I don't see this technology coming in the next few years. As I said, given the complexity of the operational design domain, you might have it in the next 4 or 5 years, or you might have it at least you'll have to wait for another 15 years. So if you're talking maybe, let's say, going from your house to the city center and there is a low speed application around available, that might happen in the next 4 or 5 years. But more complex operational design domains will take a lot of time. Unfortunately, that is the state of the technology right now.
Thank you. Anyone else got a question? Well, in that case, it just remains for me to thank you very much for a really interesting talk, Siddhartha. Thank you so much.
Thank you, John, for having me. Thank you, Margaret.
Yes. I'll unmute everybody now. You can unmute yourselves and say thank you and good night and clap if you want. Thank you.
Thank you.
Okay.
Thank you very much.
Thank you.
Thank
Good
you.
night. Thanks.
Thank you and good night. Well, they're going down, dropping off.
Bye.
Big people.
Ah.
Bye. Good night. Goodbye. Thank you for coming.
Bye.
Already. Right, looks like nearly everybody's gone now. Thank you so much for that. Thank you for coming on board at short notice.
No, thank you for having us. Thank you.
Yes, thanks a lot. Right,
Yeah.
over and out.
Thanks.
Cheers.
We'll see you tonight.
Yeah, ta-ra. Ta-ra, Margaret.